So I'm going to be looking at using a multi-Bernoulli filter to do unqueued detection in images for low SNR objects. And we're going to be using a likelihood function that interrogates the image directly for evidence to support or not support these objects. So I'm going to start with some motivation. I shouldn't need to motivate too much. We're looking at unqueued detection, as I said, specifically for low SNR. There's a lot of techniques that do this already. Just naming a few, match filtering and track before detect methods can do this type of thing. And we want to look at a frame-to-frame solution, so we're using a multi-target tracking method, specifically a multi-Bernoulli filter. In particular, this multi-Bernoulli filter was first proposed by Vo in 2010, looking directly at images to get data out of them. And a variation of this for SSA was shown by Dr. Fujimoto last year at AMOS, actually. So just want to make sure we give credit where credit is due. And we're going to be in particular looking at using match filters and some hypothesis tests on those match filters to use as our likelihood function. So just want to highlight the bottom of the slide. We're looking at first doing some analysis of these likelihood functions, trying to figure out what we should be using for SSA. And we're going to be looking at when do these start breaking down, how far low into SNR can we actually go with these methods. And then applying it to some real telescope data, which is always exciting. So on the left, you have the Bayesian prediction update equations, which are your general nonlinear tracking methods for a single object. When we go into the multi-object world, we can use these equations on the right. And the thing I want to highlight is that on the left, we have this xk, which represents a single state that we're trying to estimate and track. On the right, we replace that with this script x, which is a random finite set. A random finite set basically means that it's a set with a random number of objects within it, and each object represents one of the objects we're trying to track. So in that way, we can have multiple objects in our mathematical formulation. We can also account for the fact that we don't necessarily know how many objects we're actually trying to track. So in application, a multi-Bernoulli filter ends up being a bank of Bernoulli filters, which will usually be represented as particle filters. And so what we end up getting is effectively a bank of particle filters. What you would want is that each of your particle filters is tracking a single object. And then you'd also have a few particle filters, extra Bernoulli filters running in the background that are searching through the space that you're considering and trying to find more objects. So you're always continually doing a search for these objects. You're also going to have a birth model. That's how you're going to generate new Bernoulli filters. And I'm not going to go into that anymore. There's a lot of work that's already been done on that. And we're not really looking at that for this talk. So the two likelihoods that I want to talk about are shown here. The one on the left is the classic likelihood ratio. This is the one that all the previous work has been or has used. And effectively what it does is it says, okay, given a state, you can predict what pixels should have what values from that state. Then you can take each of those pixels and say, okay, how well does that match against what I would expect to see in that pixel? I mean, how does the measurement match that prediction? And how does the measurement match just blind, pure noise? And so the idea is when you create this ratio, if it's closer to that predicted value, you're going to have a bigger ratio here. When you multiply that together over all of the pixels, you get a larger value, and therefore your particle filter works. So there's two main things that we want to highlight about this that we think needs to be improved. First of all, you need to estimate the total signal strength for this. Generally speaking, in SSA, especially when you're doing blind search, you do not know how bright the object is. So that's an assumption that ends up being pretty bad in a lot of cases for our purposes. The other thing is that as the signal strength goes down, the performance falls off quite quickly. We want to see if we can address that too, because it's, again, we're really interested in looking at pushing it as low in SNR as possible. So our likelihood function is going to be first based on a match filter. So similarly, we're going to say, okay, given a state, what are the predictive values that we're going to get from that state in each pixel? And then we're going to perform this match filter, which is a linear image filter, which basically gives us evidence for there being an object there. And what we end up doing is we then perform a hypothesis test on it. Our null hypothesis is that there is no signal there. It's just operating on pure noise. And the alternative hypothesis is there any signal there? Is the signal greater than 0? The important thing about this is because we're just asking, is there any signal? Is it greater than 0? We don't need to actually predict the signal, total signal strength. We still need the point spread function. We still need to predict how the relative strength of the pixels is going to be, but we don't need to predict that total value, which is something we can do. The other great thing is that both of these likelihood functions are going to end up having a tuning factor involved. For the classic one, it ends up being that estimated total signal strength. So you can modulate what you guess it to be, and you end up getting different performance for your actual likelihood. That's kind of an unintuitive way to actually do that, right? In our method, we end up using probability of false alarm as our ability, or our tuning factor there, which we think is a better way to do it. Just makes sense to a user. It also has a little better performance at these low SNR values, which is pretty useful. Okay, so we want to compare these two guys, so we ended up just doing a simulation to kind of check over a range of values how well did these guys work. So first we're going to vary over photometric SNR, because that seems like the first thing that we should definitely be checking. The second thing is for both of these guys, we're going to be checking the tuning factor for each of them respectively. We're going to be varying those and seeing how it performs as we vary that. So what we get is, we get something like this, which is our signal that we would predict, and then we corrupt it with a bunch of noise, and we get something that looks like this. And I just want to highlight with this that when we talk about SNR, we're talking about the total photometric SNR, not just the pixel-wise SNR. So in a single pixel, you'll have an SNR, which is your signal divided by your standard deviation, but you can also sum up over all the pixels that you're considering. That total SNR is usually a much larger value. And that's going to be the limiting factor for our work. So when we get large point spread functions, we end up getting to push down really low into that pixel-wise SNR. To compare these guys, we want to have some kind of performance metric, and what we've chosen is a likelihood gain. And what all that means is that we're going to operate the likelihood function on perfect signal when it's perfectly predicted what it should be. And they're going to operate it on just pure noise, and we're going to look at the ratio of those two guys. Because we're using a Bernoulli filter, it's going to normalize out the particle weights after each iteration. So all you really care about is how much better does it perform on signal versus how much worse does it perform on pure noise, and that's going to tell you how well is it going to filter out that noise. Okay, so the results we got look something like this. The central surfaces that you see on both these plots is the median response for each of these data points. So that's 50% is above, 50% is below, and the two surfaces you see above and below those are the 5th percentile and 95th percentile. So 90% of the data is between those two surfaces. The two things I want to really highlight about this when we compare these two, the likelihood ratio that we're trying to beat has much lower variance, we find. That's over pretty much all test cases. Obviously, that's something that we would like to see we're doing a little better against, but can't do everything perfectly. The thing that we're doing better is we have a lot more invariance to signal strength. So our side is a lot more of a flat line, which we like to see. We like to see it still performing well at low SNR values. We also get a little higher just general likelihood gain, which we find useful. And to highlight this a little more, we just pulled out a few slices of those plots. These are just the median responses from first the likelihood ratio when it has that perfect guessed signal strength. So this one exactly knows what the signal strength is. And that's the black line you see there. And this is for 3 probability of false alarms, the performance of our likelihood hypothesis test. So I just want to point out that as we decrease this probability of false alarm, we get better performance, but we're also increasing the variance of our total likelihood. So we're not getting nothing or something for nothing here. There is a trade-off there that you have to decide between. But we're definitely seeing that at these low SNR values, we're getting a lot better performance. We're seeing that we're able to maintain some likelihood gain when we get down to low SNRs. And of course, as you bring this guy out towards really high SNRs, you're going to see that the likelihood ratio is going to beat our stuff just hands down. But we don't really care about that, right? Because at those higher SNRs, we can use other methods that would be less computationally intense than a bank of particle filters. We really want to see, when we get down to the lowest SNRs, which one's still going to be giving us some information. So we think that's a pretty good thing for us. Okay, so now we're going to get to the fun stuff, which is the operating this on telescope data that we got. So the first data set is going to be from GT-SORT, which is a research telescope we have at Georgia Tech. It's located on the Georgia Tech campus in downtown Atlanta. If you've ever been to Atlanta, there's quite a bit of sky pollution there. So when you're trying to test algorithms that look at really low SNR, it's really great because everything's low SNR because we have so much noise. So this is an example picture of what we're looking at. The actual example that we're looking at from this data set is just doing a sidereal stare at the geobelt. So in essence, we're just scanning through the geobelt, and we just want to watch objects as they kind of pass in and out of our field of view and try to detect them. And we have a zoomed in picture here of where you see our, can't really point very well. You see a zoomed in picture of where our actual object is in this image. And as you can see, you can tell in the center of that, zoomed in image that there's a little higher, pixel values, and you can tell in the rescaled image that there's a few more pixels that are saturating there. So you can tell there's something there, but it's the kind of thing that you wouldn't really be able to pick out with your, with your eyes. And to further prove that point, this is a GIF of our actual images going frame to frame, and the actual objects should be moving from about the top center of the image down and a little bit to the left. So if you can see an object moving through there, good job, because it took me a really long time to pick out that little, box. Pretty hard to find. So we run our algorithm on it. I'm just going to give you some context for what you're seeing here. On the left, you have the full image, and all of those diamonds are the maximum a posteriori estimates from each of our Bernoulli filters. So you see a bunch of green ones in the background. They're all going to be bouncing around, and those ones are just the background Bernoulli filters that we're running to try and do search and find new objects. And once they turn blue, that means that the probability of existence has gone beyond some threshold, and we said, OK, we've definitely found an object. And as you can see in the bottom there, that was the object we were trying to track. And unfortunately, it was a EchoStar satellite, and we just got it as it was leaving the field of view. Conveniently, though, our field of view was wide enough that we actually saw the next geoslot over. It was a DirecTV satellite come into our field of view. We didn't even expect to find that, and our algorithm just spat out, hey, you have another object here. So again, if we're trying to do blind search, that's really nice because it means that we are finding things that we didn't know were there. So the one thing that we are kind of cheating with here is that we're assuming inclination on the object. We're assuming that they have a low inclination. So we're saying we know where the geobelt is, so we can say that all of our objects that we're going to find are all going to be moving about in the same direction and are going to have about the same velocity, right? Now that's basically saying we assume a velocity model. We assume we know the velocity. So we're going to do another test where we're actually going to assume that we don't know the inclination. It could be going at 90-degree inclination. It could be going retrograde for all we know. We're just assuming that we know the velocity. We know that it's going at some geo or geo-like velocity, so it's going to be having a certain rate through the image, but it could be going in any direction. And so what you see is we still track both of the objects. It takes a little longer to see that top one, but that's OK because it eventually does say, yes, we're 100% sure it's there. And the thing to keep in mind is that this method is not going to get you your very precise detections. It's not going to be the kind of thing that you want to use these detections and then feed it into your algorithm or orbit determination. This is really trying to efficiently search through these images, and then you can switch over to like match filters or track before detect or whatever method you want to then do that precise locating of the object. So it means we're still finding the objects even with no assumed inclination, which is good. So the next example that we're going to show is using the Rakanzo sensor. Rakanzo is a small sat that's going to be launched into space by Georgia Tech. And it's going to be doing SSA operations. What we did was we took the sensor and lens off of it and just mounted them on a tripod and just looked if we could see anything in the sky. The actual sensor is about 30-degree field of view, so it's a very wide field of view, so we could use it, would simulate something like a search sensor, we'd think. And the great thing is that when we were trying to do this, turns out back in March, the Hitomi Astra H satellite actually had a spin instability, I think it was, and it actually had a breakup event. And 3 days after that occurred, it was still spinning quite a bit, and we were able to capture that with this sensor. So you can see here on the right, we have the, on a logarithmic scale, the photometric SNR of this object over the pass, and you can see for a couple frames it goes down below 2 SNR, which is something that you'd never really be able to see, and most frame-to-frame detection methods are going to drop it for those frames. It's not going to get any detection. When we run our algorithm on it, it finds it pretty easily, has no problem. And the key thing is, as that SNR drops down and the object disappears, we actually still track through. So you can see on the top right, we have a couple contours from our actual Bernoulli filter that's tracking it, and you can see that object disappears in the center, kind of reappears a few times, and then gets bright again, and we track through it, no problem. The thing that I really want to highlight here is that first, our likelihood function that we're using doesn't assume any brightness, and this is highlighting that fact that a lot of times we have objects that have very variable brightness, and we tried to assume a total brightness for that object, we'd be making a bad assumption. The other thing is that with most detection, frame-to-frame tracking algorithms, they wouldn't get any information from those frames where it's below some threshold SNR. Because our algorithm can just take any information the image has available, even at those frames where the object is below some threshold SNR, we are still getting some information. It's still saying, yeah, there's a little bit of evidence that there might be something here, so it keeps the algorithm tracking through once it has that good estimate. Okay, so I'm just going to go through a few conclusions. So we're doing frame-to-frame tracking of space objects. We're able to push down to quite a low SNR, especially with that photometric SNR. Try and push it down as low as possible. We're able to incorporate some prior information when we decide that we want to include inclination or some velocity models. It incorporates right into it, which I would argue is a strength of the algorithm. We don't have to worry about. If we have prior information, we want to be able to use it. We want our algorithm to do better when we actually know something about the object we're trying to track, which I think is a very useful thing. And the other thing is that variable photometry has no problem with our algorithm. It just tracks through it, no problem. I want to thank Dr. Kohei Fujimoto and Dr. Brian Flewelling, who both had gave a lot of insight and help into this project. Dr. Ryan Coder, the session chair, who built the GT SORT telescope. I would not have data without him. Andris Jaunzemis and Shez Virani and the entire GT SORT team all helped get me my data for this. I wouldn't have any data without them. And the AFRL Scholars Program and NDSEG Fellowship both partially funded my PhD work, which this is part of. These are all the great projects that Georgia Tech is doing for SSA, all of our hardware projects. And I will take any questions with that.
Okay, we have time for about 2 questions.
So I was actually curious about this case where you're building up so you don't have your particle model beforehand and you're building it up. And then how much of that, okay, so you could see in one of your images, it wasn't tracking to begin with, and then it kind of caught it on the last 2.
Yep.
And so how much information is being carried over from epoch to epoch? And so is it like you're summing the log likelihoods between epochs and you're building up that information, or how should I be thinking about that while it locks onto it in one epoch and then it's easier for it to detect it in the next one?
Yeah, so as of now, it's just a pure particle filter. So each of those estimates is coming from a block of 10,000 particles that's trying to estimate that particular object. And so once it gets a good fix on an object, it's resampling all of its particles right near that object. So what it ends up doing is all those particles get propagated to the next frame. They're all right next to the object again, and so it converges on the object. And the only problem is that when it's at lower SNRs, you have difficulty where it might be seeing multiple objects, or it might be seeing a star in one frame, and it's deciding I have multiple places I'm looking. So it sometimes takes a few frames for it to actually converge to the actual object.
Okay, let's go ahead and have the speaker.
Okay, good afternoon. I want to first say that a couple of our collaborators are here at AMOS as well. So in the area of track prioritization component that I'm going to talk about, we have both Penny Axelrad and Dr. Brandon Jones here, and so they can fill in technical gaps. This is mainly an overview of this research. Where's my advancement? Next slide. Okay, thank you. So I think the general consensus, if you ask the experts about this topic, is that even with improved automation of the SSN, it's really not possible to keep pace with the anticipated future congestion and contention of the orbital environment. And so, really what we need is a scalable solution for incorporating non-traditional sensors into the mix. A configurable software architecture that allows those to be brought in and progressively inserted to support that activity. Next slide. This is kind of an evolutionary roadmap. We have several COTS products that have been brought to bear to address some SSA issues. We have our scheduler product, which is really in its baseline form, a general purpose mission planning software suite. That's all right. Which button is the advancement? Green?
Yeah.
Okay. We have, and that's really tailored toward, has been more tailored toward supporting sensor scheduling from ground to space objects. We have our CPAW product, which has been used for space sensor observations of ground imagery. And then our AutoLogic product, which is a web-based capability. In terms of how we've advanced that in SSA, we have several different contracts in play, including some government customers that are sponsoring advancement of the products. Contract number 1 is something that's synergistic with the contract number 2, which is the focus of what I'm talking about today. So contract number 1 has really advanced ground-to-space tasking for that scheduler product. It's included an SSA figure of merit. It's included a track prioritization component, search tasking, inclusion of SSN sensors, all for the purpose of demonstrating this ability to actually advance the quality of support of SSA. The government customers really sponsored the evolution of CPAW for space-to-space sensor tasking, whereas before it was space-to-ground. The contract that I'm briefing on today is really all about web enabling, providing web page UIs to access capability that is from contract 1. And finally, we have an additional contract that's really dealing with ad hoc event type of response. So the operations concept of what I'm talking about is really coordinating SSN and non-traditional sensor tasking. You really can think about these as architectural features. So in terms of planning cycles, we have 2 sides, and I'll show a graphic in a little while about what that looks like. But we have the non-traditional side, which is based upon planning around the public catalog. And as long as you have standing commitments or contracts in place for SSA support, those sites can actually participate. There's an option to go from one side to the other. So if the JSPOC wanted to actually engage in tasking across the boundary to non-traditional sensors, that's possible. It's not precluded by the architecture. On the other side, you have the JMS or the JSPOC side of planning for the SSN. And it can benefit from what comes back from the non-traditional side, accounting for the gaps that need to be filled based upon knowledge of what the non-traditional side is actually doing it. The kind of novel things that we're bringing in this particular contract are really in the area of maximizing information gain for SSA. And I'll talk about those components in later slides. Another critical feature of this is sensor participation levels. And so we have these notions of 3 different modes of operations. We have scheduled tasking, where you tell sensors exactly what they're going to observe at what times. You have task sensors, which is you give what you need to observe, but don't specify specific times. And you have contributing, which is that the site is actually given a list, and it's up to them which ones they're going to pick to that list in service. The nice thing about specifying these participation levels is that there's going to be a transitional period. Most sensor sites are not really supporting machine-to-machine type of interfaces, and in that transition process, this type of arrangement allows you to accommodate any type of site and then build up from that point. Sensor feedback is an important part of this. In order to accomplish dynamic tasking, which is one of the objectives, you need to be able to have the site tell you when they have scheduled downtimes. You need a kind of confirmation cycle of we would like you to receive this tasking and have them say, yes, we'll accept that, no, we won't. And also the ability to provide back observational data, which is critical to being able to push through a data portal and actually support the SSN elevation process. And that all feeds the responsive tasking paradigm of being able to take in that information if a site dynamically or unexpectedly goes offline, the ability to adapt and run the scheduling again to be able to accommodate those types of issues, as well as identification of new objects and change in priority of events, for example. So in turn, we have an object catalog. One of those resides on either side to feed this planning process. Access management is another critical feature of this, being able to limit data visibility and access of users to certain parts of the architecture. So it's just a graphic of kind of the process flow. You'll note that really these are two process loops that coexist with a couple of touch points on either side. On the left side, the SSN sensor process is really developing a plan, committing that plan, allowing the sites to be able to confirm or reject receipt of the individual tasking instructions, the ability to be able to provide back status on the successive observations, and then pass that through the processing loop, being able to determine the orbits, characterize objects, identify new objects. Same is true on the other side, on the non-traditional sensor side, but really the points where they cross is at the junction at the top where you have a public catalog filter, where the SSN side catalog can be pushed through, subject to filtering out specific objects, and made available on the non-traditional side. And the same thing is true on the bottom side, where the non-traditional observations can be passed straight through and used at will on the SSN side. You know, notice that there's a clean break between the classified and unclassified side of this paradigm, and really there's similarity between the implementations. In fact, they're pretty much identical inside of the blue boxes in terms of the functional capabilities of what we call this Heimdall architecture. Inside of the architecture, you have the ability to fully manage configuration of the sensors and the catalogs, the ability to take that catalog and push it through visibility computations, and then do the track prioritization calculations, apply a figure of merit, which I'll talk about, and ultimately come up with a tasking solution that ends up on the non-traditional side getting pushed to the participating sensors over the internet or dedicated VPN connections. The same is true on the other side, on the SSN side, where we interact with all of those similar services through an information bus. So in terms of prototyping for this specific effort, it was built off of existing products, COTS products. The existing product that we call Order Logic is really the web enabling, the web server that allows you to get to the capability. And it already existed for the use case of space sensors servicing ground targets. And so it had the access controls in place for being able to work those issues through the web interface, and a dashboard to give kind of status display and perform visualization. So the extensions for this effort really were adding the ability to service RSO targets, where before it was only the servicing of ground targets, and the ability for ground sensors to be modeled versus the previous paradigm of only supporting space sensors. And then to actually provide tasking via the scheduler engine externally, operate the tasking cycle by triggering it from the UIs. So we really leverage SDK and our SDK scheduler product, but have applied a layer of SSA enhanced ground sensor tasking on top of that. Really the goal of all of this in the first phase of development was to get to the point where we could demonstrate the right side of the graphic I showed you earlier, which was the non-traditional side of being able to operate that entire cycle and interact with a couple of sites with the new development. So the prototype architecture is half of what you saw on the long-term graphic. And so what we did for this demonstration was derive from spacetrack.org catalog, push that into the system, and then determine plans, push them across with a couple of agreements that we had in place with a couple of actual site operators, and I'll talk about that exercise later. Just a few screenshots of kind of web UIs that you have access to. The large graphic is really kind of the dashboard. Once a plan has actually been put out, tasking plan, you can scroll down through, and there's color coding on what's been collected, what still remains to be collected. If you click on any of those, you're able to look in the 3D visualization, which is supported by Cesium, and kind of get the geometric view of that particular acquisition, what it looks like. And then management screens for administration of adding new users, adding new sites, the ability on the bottom to browse through observations that have been provided by sites. And all of this is accessible through standard web browsing. Part of this development process involved University of Colorado and University of Texas. They jointly worked on track prioritization algorithm. What that allows us to do is use a finite set statistics approach to basically perform modeling of multi-state targets, which I'll talk about on the next slide a little bit. There's an information theory associated with all of this, and the intent really is to be able to characterize the improvement that you expect to gain for a given sensor servicing certain elements. And that can work on a single target object in a scene or multiple target objects in a scene. And it can be used either for refinement of observation and refining state knowledge on a single target, or for determining regions for follow-up on UCTs when they exist. The way that we integrate with that is as a plugin, effectively. Originally, this was Python code. It was ported to C for performance improvements and parallelized. And so we've taken that a long way toward actual maturity to be able to be usable in a real context, operational context. In terms of track prioritization algorithm, just a little bit more detail. It really specifically uses this cardinalized probability hypothesis density filter approach. Actually, Dr. Jones has a talk on the technical details of this tomorrow morning and can provide more details in line in presentation. The inputs really are providing candidate sensor tasks and catalog estimate. The outputs are information gain that you would expect from various observations, estimates of the number of targets, the density of targets and function, and you can use that to support observing in certain areas or to determine that you would not want to point in that because of certain characterization out of the algorithm. We leverage COTS modules. I talked about those a little bit. We do use SDK. We drive these with APIs from the order logic product. So we use an API over a TCP protocol to actually control that from the order logic product. SDK models ground sensors, sites, constraints, space targets, computes basically constrained observation opportunities. I had mentioned our CPAW product before. That is used to specifically support the space-to-space observation side of this, and both of those can interact and operate through the order logic interfaces. Scheduler product is similarly accessed through an API, and the SSA functionality associated with that product is achieved via a license plugin. And again, it just allows generic definition of resources and constraints. You can specify sensors and targets that are participating. Tasks come out of that and are bounced against scheduling constraints to determine an optimal optimized prioritized schedule solution. And we make calls out, as I mentioned before, to the CU and UT track prioritization module for that target density. A little bit about the figure of merit scoring. When you're applying the figure of merit to determine optimization of the schedule, you're looking at age of previous observations, for example. You're looking at covariance. So those are the kind of inputs that are taken in the figure of merit. Also noteworthy to mention that in terms of the ability to tune the figure of merit, there are a few controls that can be applied at the level of balancing search tasking versus target tasking, so you can kind of shift the relative priorities and normalize those two tasks depending on the current state of affairs. You can also balance independently the controls for space-based sensor tasking versus ground-based sensor tasking, so there's really a lot of ability to fine-tune the architecture. So our phase 1 tasking demonstration was reaching agreements with AGI's ComSpoc and also the Air Force Academy's Falcon Telescope Network to participate in a validation of the architecture capabilities. We did this back in January from our offices in Greenbelt, Maryland, and all of this was run from our web UIs. So we had a configuration that was loaded up. We had a catalog where we picked a couple of targets. We optimized the schedule. We were able to review that as an administrator before releasing those. The tasking was developed by an email-based interface to the sites. The sites took those requests. They attempted to make observations. They confirmed that they were going to attempt to make the observations. They provided the observation status back from those. We collected those, received confirmation, and we were able to display observation data, which was uploaded by secure file transfer. And the whole process was managed by kind of a Heimdall operator oversight. Unfortunately, the weather conditions at both sites really were not good that night. It was cloud cover, so we didn't really have successful observation occur, but it was a good verification of the end-to-end data flow between all the elements of the architecture. In terms of next steps, we were just released for phase 2 of this effort earlier in this week, so we're at the point of getting going on this. These are the kinds of things we're going to be working on, and in fact, there's synergistic work for what's happening on the JMS side through another contract that we're actively working on, and we've made good progress on working that left side of the graphic for the SSN as well. And I guess I would offer that we're very interested as we move forward in speaking with those who are developing sites or currently operating sites that would like to participate in going forward in supporting testing to elevate the maturity of this paradigm. And so with that, I'll close out and offer to answer questions.
Okay, so we have time for a few questions. And if there are none, let's thank the speaker.
Good afternoon. I'm Jeremy Raley, as introduced. I'm the DARPA's program manager for the Orbit Outlook program. And, I got the right one, I hope. So I'm DARPA's program manager for the Orbit Outlook program. So this program is actually coming to the point where it's winding down, but I want to talk to you about some of the accomplishments that have been made throughout the course of this program, as well as opportunities for transition and future use of it. Right now, what I'm going to talk to you about is DARPA's overall view for battle management, command and control for space, and then talk about where Orbit Outlook takes the traditional way we do SSA and tries to add some innovation to that, and then of course how we're going to go forward and make that applicable to some of the problems we've been discussing here for the last few days. As far as DARPA's investments, there's several. There's the sensor-centric part, so Space Surveillance Telescope. I know that's been talked about a few times. Dr. Lindsay Millard is, well, I think she's gone by now, but she was running around here, is the program manager for that. So there is a need for exquisite new sensors. There's the data-centric part, which is where Orbit Outlook falls. So if we can demonstrate the ability to use non-traditional sensors and overcome some of the uncertainty involved with that so that that becomes useful data for us, then that's our data-centric approach to it. And then as we move forward, you move into other programs like Hallmark, where you say, okay, what's the information coming out of that once I've taken that, I've used exquisite new sensors, I've obtained data, what's the information coming out of that that's going to allow a commander to make a decision or a commercial operator to make a decision to burn fuel and do something about whatever's going on as far as the situation in space. Obviously, being from DARPA, I'm a little bit military-centric, but you can see how it applies in other domains. So space situational awareness, I'm not going to read the top right of the chart. I think everybody knows about that. But what we're trying to do as far as unique capabilities from the Orbit Outlook program are to couple non-traditional sources. So what that means is, can we go buy data from someone rather than having to, the government having to take on the cost of building designing, building, going through the requirements process, fielding, maintaining some exquisite sensor site. Obviously, if we only need data in certain situations, we're feeding a mule we're not going to plow with an awful lot there, to use an old country expression. And then, of course, once we have these kind of capabilities, they're non-traditional. How can we use them to enhance the space surveillance network? And one of the chief ways is how do we free that up to do its main mission and allow this to either tip and cue that or allow it to take on missions that are considered less critical than those where these exquisite sensors, such as those in the SSN, are required. The overview of the Orbit Outlook program this is the one slide that kind of captures it all. So what you see over there on the left are the variety of new and novel data sources that are being incorporated. The first one up top there is Stellar View. So getting data from universities is a good idea. There are many academic telescopes out there that do a great job of making astronomical observations. They know what they're doing. Now, are they trusted and certified by the Space Surveillance Network? No, so there's some work to be done on the data there if it's to be used for military space situational awareness applications. Are they necessarily trusted? No. They may not even exist inside the United States or one of our allies. These are just observations that we could bring in. The second one is Space View. These are amateurs. So these are people who may not even have their telescopes completely calibrated or have the ability to do that. However, they are making observations of the sky. And so we went to one of our industry partners and said, hey, can you get some people together that have decent quality telescopes, some of them literally in their backyards, actually most of them were under that, and buy the data that comes off of those, bring it into Orbit Outlook, and use that to help. As you can imagine, that would have some advantages as far as geographic diversity, because you can buy this kind of information from wherever amateur astronomers like to set up. LELO was a very specific application. That's low inclined LEO satellites tracker, and so that's almost an optical fence. That one was tested and is now actually in pieces on a barge toward Ascension Island because it was tested to make sure it functioned, but now we'd like to actually put it near the equator because the low incline part of that implies that you have to be near the equator. Government and military sources. Obviously, if you're going to do something like this, you'd be foolish not to suck in all the data from SpaceTrack, right? And so that's a big part of this, is bringing in that data. It's fairly well trusted, but not completely trustworthy, as I'll show on a later slide. It's freely available and is updated regularly. There's also, NASA provides precise ephemeris for certain satellites, so bringing in that data as well helps you to understand, helps you to calibrate, and of course, is useful as part of the program. EchoView, we started bringing in radar data as well. So being able to bring in multiple phenomenologies, and as you'll see, we exploit that even a little bit more with some of the algorithms that come in. And then ComView was where we were doing data buys from ExoAnalytics. As I mentioned before, being able to buy a block of data and bring it in as needed is an advantage for the government because it prevents us having to go through our processes to procure the infrastructure necessary for that. So I've talked to you about bringing in a lot of data, so it's becoming kind of obvious that what's going to happen is there's going to have to be a database. And I promised you at the beginning it was a data-centric project. So what we're talking about here is bringing that into the Orbit Outlook data archive. So that's great. It's all sitting in one place, but what are we going to do for it? We're going to utilize the Orbit Outlook data processing algorithms, and you can see those around the outside of the archive there that go in, and I'll go into a little bit more detail on selected ones of those, but these basically reach into the database, pull the data out, operate it in some way, and then put it back with an annotation. There is heritage there, so the system maintains lock on what was done to data, when, and where various confidence estimations and those kinds of things come from. At that point, then you want to be able to do something practical with it. So knowing where something is great. Knowing where it's going to be is, makes it useful. So orbital prediction, size, shape, and attitude. So you can get the actual characteristics of some of these space objects based on radiometry or astrometric observations. And then, of course, the feedback loop that allows you to close this, I did say it was a data project, is going back to those sensors, and if by combining this multitude of sensors, one of the things the algorithms allow you to do is come up with a more precise estimation of where the object is and its state vector, where it's going to be. So if you have an observer who's feeding you something off, it's either biased or skewed somehow, you would like to be able to feed back to them and say, hey, especially if they're one of those amateur astronomers, perhaps you should perform a calibration, or your data is consistently skewed. That also helps the algorithms themselves know how much confidence to have in that particular sensor as time goes on. So it's like people. You learn to trust certain people and you learn to distrust certain people. Operations that consist of the basic steps here, and I've really gone into a lot more detail on that on the last one, but this is just that high level. Obviously, we're bringing in a lot of data. The more data we bring in, the better, and the more opportunities we have to detect events that happen outside the view of traditional sensors, or when traditional sensors aren't cued onto an asset. The next piece of that, because all that data comes in and we've kicked the can down the road as far as caring about the quality, is how do we validate that data is true and combine sources of data to actually obtain information and pull useful, actionable information out of that. So one of the key things here, as I've alluded to several times, is increasing the number of observers. The advantages of that are fairly obvious. If something's going to maneuver, particularly if it's going to attempt to maneuver when it's outside of our known view of, say, space surveillance network sensors, then having more sensors, having a geographic diversity of sensors, having sensors that are taskable on an ad hoc basis, or data that can be bought when needed, is a huge advantage of that. This also makes the program a lot more scalable. All of a sudden, if a bad event happens in space, there's some kind of breakup, there's some kind of propagation of debris, and the United States government decides we need a lot of observations right now to try to keep our remaining assets safe. This is a good way to be able to free up, to scale up quickly. And then, of course, as I mentioned before, it frees up the space surveillance network to do critical government-centric tasks, while these other things can either tip and cue that, or be tasked to do lower priority, or tasks where the amount of trust in the sensor can afford to be less. And then, of course, once you do that, you're going to have to bring that back into the database and talk about all this in a common language. And so that's one of the other challenges, is how do we bring these multiple observations back into one place and be able to talk about them rationally. And then, of course, having a database is great, but people need to be able to both access that and get the information they need, as well as put information in there. And so setting up those sharing relationships, very easy in a technical sense. I have a software guy that works for me. It's like, we're pushing data around. Yes, we are. But there's people involved in that too, people with expensive assets on the line. And so there's that element of the program as well. As far as how we organize and store the data, I've talked to you about the data providers. The only information they actually have to provide from this list at the top of the page there is a timestamp and the actual track information. This is not mandatory, so we do not mandate a format. Now, those would be known as unsophisticated providers, and we try not to use the term derisively, but we do have to figure out how to pull their data in and fill out the rest of that, and how confident we can be in that data. As far as the algorithms go, those things reach in and touch that data to help us move from, pardon me, move from where we expected an object to be, how we expected an object to be reported from a certain sensor, just to be clear, to where do we actually think it is, and go through that whole feedback loop I described before to where we can update the catalog or tip and queue the space surveillance network to update the catalog. Might be a future ConOps. That's not something that's going on right now. Report incidents like a maneuver, as well as feedback to that sensor and say, let's make the system better as we go forward. As far as data processing, again, we're bringing in the data, we're making sure that it's actually valid data, that it tells us what we need to know, and that we can act on that. A couple of processing algorithms that I want to highlight are Padme first, and then Vader will be the second one. And I've been promised that the Star Wars names will be gotten rid of if I ever transfer it, but for now, we're sticking with them. Padme does the astrometric processing, so it goes in and says, where did we expect the object to be? Have we seen a change? It runs through this loop and figures out what object it is. It allows us to also detect if something's an outlier, and that's where we can also tell if a sensor is off track, needs calibration, or some other kind of maintenance. Vader is the radiometric observation of that. Very similar loop. Does this object, if we think it's a certain object, does it exhibit the same characteristics that it did the last time we observed this same object? Or do we need to lay down a pattern of life for it because it's a new object that's coming in? Where this is very practical is that it quickly identifies if something's been cross-tagged. So I alluded before to getting reliable information from SpaceTrack. When that comes in, occasionally something gets cross-tagged, and if things go way out of family with respect to the radiometry of the object, you can look at it and go, that's probably cross-tagged with another object that used to have that same radiometric characteristic, and you can deconvolve those and fix that very quickly. What we're going to do next is test the system with synthetic data. Johns Hopkins University Applied Physics Lab is making up the data, keeping that away from the providers, and then fuzzing the data with errors typical of the quality of astrometric observations that we've been getting from the data providers that I showed you before. That'll allow us to feed massive amounts of data into the system and let it operate in an automated fashion to see if we get what we expected as far as the benefits of being able to get confidence from this, and to take this untrusted data and start pushing it, start lowering the error bounds around it and getting actually more precise estimates of position and orbitology on these objects, the fake objects, admittedly. The transition path for this, again, as I talked about before, this kind of goes back to the beginning of getting additional data, figuring out whether we can trust that data, figuring out how to use that data to make decisions, and then moving beyond that to do things like indications and warnings in a more automated way, because the system does understand more about what's going on. So, so far, we've kind of come through the program. We've integrated live data feeds, and this is sort of a simulated live data feed. We've taken live data, gotten it all prepared so we can put it into the system quickly. We've successfully demonstrated the components on a one-by-one basis. Compartmentalized there, has nothing to do with multi-level security or anything, just to be clear. And now we're entering a period where we're going to do 1 month data ingest and then a month of data analysis to test out the system with a view towards transition. Thank you.
Yeah, we've got time for a few questions.
Data quality is affected by a variety of things like timing errors, reference frames, various corrections. Do you just try to determine whether data is good or bad, or do you try to narrow down why it's bad or how it can be improved?
So what we're trying to assume is that there's no a priori knowledge of the object itself with respect to these observations. The way that you determine whether a particular instance of data on a particular object is good or bad is by allowing the algorithms to run, fusing those observations into a precise estimate, and then going, hey, these guys were the outliers. Maybe it was a bias, maybe it's a miscalibration, something like that, and then pushing that information back to the data provider.
Right. So you can have a feedback loop. A bias is not a good thing, but then if you correct for that bias, estimate it, you still have information in the data that would be useful.
Yes,
right? Okay.
absolutely. Yes.
Just to follow up on that a little bit, how much of this data is calibrated against external absolute references, like precise orbits given a priori? I mean, can you really qualify the true accuracy and precision within Outlook?
Within Outlook, not any more than what you're calling your most trusted source. So perhaps if you look at data against the selected satellites for which NASA provides precision ephemeris, then you can look at those. But that's why we're doing the test the way I described, where we're making up all the data so we know the absolute truth, then we fuzz it, and then we see how close orbit outlook with these simulated multiple observations brings us back to the known truth that we started with. Anything else?
Okay, let's go ahead and thank the speaker.
All right. Well, thank you everybody for being here. I'm going to be talking today about some work that we did, or we've been doing, on applying evidence-based reasoning to sensor tasking for space domain awareness. And in particular, we're trying to really focus on how the role of the decision maker can play into this and how we can plan to help decision makers and support them. So I don't really think I need to go over space domain awareness, but suffice it to say that we're focusing on, in particular, this actionable knowledge portion. We're trying to gather information that we can use to make decisions in the future, or so basically, we're trying to gather information that's actually usable, not just more collections, I guess. A lot of the current tasking techniques focus on maximizing information gain, as we saw a couple talks ago, or minimizing covariance, for example. But we wanted to sort of take a step back and look at this problem from a decision maker's point of view, and look at how the tasking that we are using, or that we're enforcing on our sensors, how it impacts decision making and sort of what that loop is there. It turns out there's a real-time rolling interaction between decision makers who are looking at the landscape of available hypotheses and the priorities that they're assigning to them, and trying to figure out which ones they should be going after to help in their decision making. And then the actual sensor asset schedulers who are looking at the priorities that have been given to them and trying to figure out how they can task their sensors to resolve these hypotheses for the decision makers. When I'm talking about hypotheses, I'm sort of talking about like very more general statements, I guess. Like, is the zero effort miss distance between these two objects less than some threshold that I have? Or if I've tried to observe an object and I've missed that observation, is that because it had some anomaly that I need to figure out, right? But sort of, again, stepping back into just a general decision-making context, the goal that we're trying to approach here is making timely decisions in highly constrained environments. And so the first thing that we want to do is to develop decision quality hypotheses. I think the keynote speakers yesterday did a good job of sort of highlighting this importance that we really need to be gathering decision quality information, and in particular figuring out how we can use our sensors to interrogate these hypotheses. An important thing that we wanted to address here is that not all data that we gather can carry information on both, I guess, the truth and falseness of a particular hypothesis. When you're looking at it from an analyst's point of view, not all evidence, I guess, can observe that full spectrum, right? There's sometimes some level of, I guess, ambiguity is the best way to say it. So the evidence that's provided to you might not be able to fully say, I guess, with exact precision, well, what the probabilities are, and there might be some sort of ambiguity that's involved in there. So how can we, I guess, implement an algorithm that is able to account for that? And we're going to call this measure ambiguity or ignorance as we keep on going. But when you look at, I guess, these three probability measures that you have now, truth, falseness, and ambiguity, how can we work to drive ambiguity out of our system and arrive at the actual true probabilities for each of these hypotheses, right? That seems to be a reasonable way to task our sensors. We want to be able to figure out what the true state of the system is. So that's kind of our approach then. We're going to assign sensors to resolve these decision quality hypotheses that we've generated based on driving ignorance out of the system. And of course, there's some associated time constraints and maybe some priorities that are being provided by the decision makers. The particular approach that we're taking, again, is to apply evidential reasoning in this particular case and apply it in an optimal, I guess, a multi-objective optimization problem. So to describe a little bit what evidential reasoning is, it's easiest to just contrast it with what everybody knows and loves, which is Bayesian reasoning, right? And in Bayesian reasoning, again, you assign a deterministic value to either truthness or falseness of a particular hypothesis. But again, it's not able to account for ambiguity in information sources. So the problem that arises is that lack of evidence from a particular evidence source is not necessarily equivalent to evidence to the contrary of that hypothesis. This is not like a new criticism that we're coming up with or that even Schaefer came up with in his text. It's been around since Bayesian reasoning was introduced in the 19th century, right? So this is nothing new, and we just wanted to apply this different construct that Schaefer made, which is called the mathematical theory of evidence, using Dempster's theory of, I guess, probability intervals. It sounds, I guess, it sounds like it could be scary or different, but it's really not that much different from Bayesian reasoning. You start off in the same place, basically. You have a set of hypotheses that you're interested in interrogating, and then you formulate mass functions that assign or that map from this hypothesis space that you have to the 0 to 1 interval, just like a probability. The main difference, though, is that you're allowed to attribute belief mass to subsets of hypotheses. So it's kind of equivalent to saying, I believe with probability P that it was either A or B. And in saying that, as an expert, I'm saying that I'm not able to delineate between these two, right? So I'm admitting some sort of level of ignorance in specifying between these two hypotheses. That's kind of the strength, I guess, of Dempster-Schaefer. Using these belief mass functions, you can then formulate or compute a direct support value, which is the belief. The plausibility is considered the support that's not directly contrary to it, I guess. And then the ignorance is the difference. So the bigger the gap between belief and plausibility, the less you understand, based on your available evidence, what the true probabilities are of the system. So once we have a mass function from a particular expert, we can then combine these, pull up the evidence using Dempster's combination rule, which works to normalize out the conflict between these belief mass functions. And I guess the important thing here is that you need to make sure that you're combining independent pieces of evidence so you're not overweighting one particular piece of evidence over another. When I'm talking about evidence, I guess, in SDA, the particular evidence sources that we have available to us are, for example, all-sky cameras, which can be always looking at the sky and performing some sort of cloud detection algorithm, or bots that are scouring the internet and looking for RSS feeds or social media posts or something, or even just weather forecasts. But in particular, we're also very interested in these taskable sensors, which need to be directed. So how can we formulate basic belief assignments to, I guess, guide these particular sensors to interrogate the hypotheses that we care about? So, we have this optimization problem in front of us. We have a set of actions that we can take, and we have a set of hypotheses that we care about interrogating. So we put forward, I guess, that a reasonable way to approach this problem is to try to drive the ignorance out of the system. So we want to achieve a minimum ignorance state at some future time. The problem, though, is that we're dealing with very nonlinear dynamics. We're dealing with a highly multi-objective problem, based on how many hypotheses that you care about. These decision variables are oftentimes very discrete, so you have mixed integer optimization. There's optimal control involved in actually tasking these sensors, and each of these particular sensors can be thought of as its, I guess, own standalone NP-complete problem, right? So all of these words are kind of meant to say that we understand this problem is really hard, right? But the particular tact that we're taking to it, we think, is very intuitive and And again, from a decision maker's point of view, straightforward way to formulate the problem to try to attack the hypotheses that they care about. What we're doing here is allowing the decision makers to assign priorities and then minimizing the weighted total ignorance. And so by changing these priorities, you can sort of move along a Pareto surface defined by all your n hypotheses, I guess. And so that's kind of like the multi-objective portion of this. So up to this point, I've kind of been saying a lot of general things and sort of trying to frame the problem in a very general manner. But I want to try to make it a little bit more tractable and approach it from a low-dimensional standpoint. So we've concocted this scenario that's very similar or very familiar in space domain awareness, where we have the competing hypotheses of trying to track a couple of satellites and then trying to search for new objects that are not currently in the space object catalog. And so I want to walk through how we actually formulate these hypotheses, how we can make basic belief assignments that we can then use to interrogate these hypotheses, and how that actually informs our sensor tasking. In particular, in this case, we have a LEO spacecraft that we've been told to keep track of and a GEO spacecraft that we've been told to keep track of. So the first thing we need to do is we're going to attack the search objective and formulate a hypothesis space for that. And in this case, it's a very simple binary hypothesis space. We looked in a search area, and we either did detect a new object or we did not. Keeping everything into like a binary hypothesis structure simplifies the math a little bit and makes it a little bit more computationally tractable. So that's preferred, I guess. As far as evidence that we can use to develop basic belief assignments, we constructed a PDF of, I guess, space object density based on the space object catalog, and then conditioned that on solar phase angle. So these are the things in the space object catalog that have the best observation conditions at the current time. And if you look at the plot on the right, so this is a look angle plot where the middle of the plot is directly overhead, an elevation of 90 degrees. The top of the plot is north, the bottom of the plot is south. So you can see up in the sort of north region, also this is from the Georgia Tech Research Telescope, Space Object Research Telescope in Atlanta. So if you look north from Atlanta, obviously you're going to be looking at the poles. And if you look at about 30 degrees above the horizon, you're going to be looking at this very dense region where a lot of these polar orbiting objects are passing each other. So this makes sense. This is what our PDF is showing us, that that's a good area to look based on highly observable and highly dense regions of space. You can also sort of see the equator area and the geo belt pretty much down at the bottom of the plot. On the other hand, we have the track hypotheses. And again, we're going to formulate this as a binary hypothesis problem where we have, if we've tried to detect our track object, we either did detect it or we did not detect it. There we go. So the evidence that we can use to formulate a basic belief assignment in this case, we have a couple different things that we're looking at. For example, the elevation needs to be high enough that we can see it over the Atlanta skyline, for example. Or the observation conditions need to be good enough that we predict that we'll be able to detect it based on sky brightness and cloud cover and other such things. And also, this is where we kind of get that covariance portion back into it, right? We want to keep the covariance small enough so that when we try to look at it, we have a high probability that we're actually going to see the object in the field of view based on what we know to be its uncertainty at the current time, right? So all these things can be sort of folded in as different basic belief assignments. In the simulation, we're propagating these spacecraft along using SGP4, and we're keeping track of the covariances using an EKF. So I'm going to show a couple different simulated results now. So in the middle, we're seeing the simulation as it's progressing through its 20 time steps. Each time step is a minute long, and the sensor is allowed to choose between tracking the LEO object, tracking the GEO object, and searching for new space objects. And remember, it's just trying to minimize weighted ignorance. And in each of these cases, the weights are equal. So it's really just trying to minimize ignorance, right? In this particular simulation, the sky conditions are clear and dark. So observations, or I guess the probability of detection for each of these spacecraft is always very high. And the time step, I guess, it's only allowed to look at the current time step. It's a greedy search algorithm. It's looking and saying, at this current time, what action is going to allow me to reduce my ignorance as much as possible? So you can see what it does first. In that first time step, it immediately tracks the GEO object in the bottom left, and it reduces a bunch of ignorance because it detects it, right? And then it starts looking for a search, or through the search pattern area, because it senses that it could detect or could reduce a little bit of ignorance each time. The probability density in those areas is still very small, even though it's the densest area of the sky. It's still a very small number, right? So it can only reduce the ignorance a little bit each time. But then when the LEO object comes above the horizon, it figures out that, hey, here's another object that has high ignorance. I can reduce it by trying to detect it. So it goes, finds it, reduces the ignorance. Then a couple steps later, the covariance has changed. The observation angles have changed a little bit. So again, now the covariance has exceeded, or is going to exceed, the field of view of the particular sensor that we're dealing with. So it goes back and checks it again, and then it goes back to searching, and it goes back to checks it again. So it kind of oscillates back and forth. And so the way that we then handle this oscillation problem is by adding in a receding horizon. So now it's able to look 5 time steps ahead and say, okay, at the 5th time step from now, I want to have the lowest possible ignorance I can. What are my possible options? And so we sort of brute force analyzed all possible permutations of this. It's 3 to the 5 possible options at every time step. Again, it does the same thing. It seeks large ignorance reductions by looking at the GEO spacecraft first, and then going to search for a little while, checking the LEO spacecraft when it comes above the horizon. But then the interesting thing that it figures out to do is it waits until the LEO spacecraft is about to leave the field of regard. In the very last time step that it can observe it before it goes below the horizon, it checks it again. So this allows it to sort of keep on continuing to search. And we just thought this was an interesting result. We didn't tell it mathematically that we want it to search more, for example. It just figured out that it can reduce a lot more ignorance all at once just by waiting until that last time step. In this particular case, it's similar, but we've added some cloud cover in the north. So it's a very similar result, except that this time it checks it right before it goes into the cloud cover. So it realizes that its probability of detection is going to drop as soon as it enters the cloud cover. It's going to, if it tries to observe then, that's I guess an ambiguous result. It's going to gather some ambiguity in its observation. So it tries to detect it, or it does detect it right before it leaves through the clouds. So these are just some interesting results that we're getting from these preliminary simulations. So again, what we've presented here is a framework where we can develop decision quality hypotheses and try to interrogate them using the available evidence. By using Dempster-Shafer theory, we're able to address sort of maybe a weakness of Bayesian theory that doesn't allow us to handle ambiguity, and also allows us to formulate this as a multi-objective optimization problem where we're trying to reduce the ambiguity in the system and approach the true state of the system, the space environment that we're observing. In the future, we're going to be looking at, I guess, examining that Pareto surface and trying to figure out, what kind of sensitivities we can glean from the current weighting scheme, and how, if a decision maker says, I want to weight up this particular hypothesis more, what is that effect going to have on the sensor tasking and the available data that's coming in. And additionally, we really want to address this computational tractability problem, where as you get more hypotheses that you care about, as you're looking further in time, you're going to have, I guess, an exponentially growing problem, right? So we want to find those particular actions that map from one action to many different hypothesis resolutions. So maybe observing one particular spacecraft can help improve its conjunction analysis and also improve its next detection probability. So those are the kind of things, the low-hanging fruit that we want to go after in the sensor tasking. So with that, I'll leave up again this slide with all the GT or all the Georgia Tech hardware programs that we have, and I'll have any questions. Thanks.
Okay, we got time for a few questions. We'll start with you.
Yes, you have mentioned multi-objective at the beginning, and then you just use minimized weighted ignorance.
Yes.
So you have reduced the multi-objective down to single objective?
Well, so we're choosing, I guess, to handle the multi-objective problem by allowing the decision maker to prioritize different, I guess, hypotheses over each other and minimize certain ignorances more than others, I guess, right? So by changing the weightings, you can move along that Pareto surface.
So basically, you have to solve the problem multiple times to be able to trace the Pareto front.
Right. That kind of gets to the computational tractability stuff that we want to look to in the future. Right now, we are brute forcing, the entire solution to figure out what possible options you could have. But in the future, we don't want to do that, obviously, right?
I would recommend multi-objective genetic algorithm because it can trace out the Pareto front in one fell swoop.
Okay. Thanks. Yes.
Hi there. In looking at your description, it's an eloquent method, but myself, I'm in the operations community. I think you're struggling with a problem that we don't really have a lot of application for. There is one that if you could solve, I think we would buy your mousetrap. That's when you have transfer orbits. There's always a family of transfer orbits, and you want to reduce the amount of uncertainty of that family as time goes on and different sensors contribute.
Okay.
That's a classic, right now, network problem. Your method looks like it might apply to that.
Okay. I appreciate that. I'll look into that.
Suggestion.
Absolutely. Thanks. Any other questions?
And if that's all the questions I have, I thank the speaker.
Thanks.